Welcome to the lecture on motion transmissibility. So, we already discussed that we use the vibration isolators to reduce the transmission of the forces or motion from a machine to the foundation, or if to reduce the motion when some sensitive instrument or sensitive item is put on some base, some where there is some vibration from the base. So, we can see that the this motion transmissibility, also we call it displacement transmissibility. So, it is the ratio of the amplitude of the response x to that of the amplitude of the support. Okay. So, let us see here, there is some sensitive instrument M is kept on some surface, okay, and that surface is vibrating with some harmonic way, and so this motion is going to affect the response of this mass, and so we have to keep these isolators, okay, so that the motion from this base is least transmitted to this mass, and so the here the role of the displacement transmissibility will come. So, let us discuss this. So, we have this system. So, we have a mass, okay, and here we can say this is the support, but this support has some motion, it has some motion. So, okay, so this support is moving, it is vibrating. So, this is a case of the support, similar the case of the support vibration, and we can do the analysis by making the free body diagram of this mass. So, this is the mass, and we have, because this spring will be compressed by x minus y. So, the net force on this spring is k times x minus y, and similarly the damping force is c x dot minus y dot, and here this is x double dot. So, we can write the equations of motion. So, here mx double dot equal to minus k x minus y minus c x dot minus y dot. So, we can write mx double dot plus cx dot plus kx equal to ky plus cy dot. Now, here y equal to y sin omega t. So, y dot equal to, we have to differentiate this. So, we can have y into omega into cos omega t. So, here we can write k into y sin omega t plus c into y omega cos omega t. So we can write k sine omega t plus c omega cos omega t. So here they are the two harmonic motions of the same frequency, and we know that we can combine them. So we have y root k square plus c omega whole square into sine omega t plus alpha. So where this alpha equal to tan inverse c omega by k, and this is tan inverse c omega by k 2 zeta r. Okay. So now we have this system, and if we compare this system with another system mx double dot plus cx dot plus kx equal to f0 sine omega t. So we see that it is this f0 is equivalent to this term, that is the amplitude, and this is the harmonic motion. So there is some harmonic force equivalence of this term that is applied to this system. And when there is for the single degree of freedom system which is subjected to some harmonic force, we have already derived the response, and the response, so x equal to steady state response, x equal to x sine omega t plus alpha minus phi. So because this is the force and some phase lag will be there here, and x equal to, if we remember, it was f0 upon k minus m omega square whole square plus c omega whole square under root. Now here f0 is equivalent to this term y root k square plus c omega square. So it is y root k square plus c omega square upon under root k minus m omega square whole square plus c omega whole square. So from here we can find x by y equal to root k square plus c omega whole square upon k minus m omega square whole square plus c omega whole square under root. So we take k outside and we will have under root 1 plus c omega by k whole square upon 1 minus m omega square by k whole square plus c omega by k whole square, and this is under root. So we can write c omega by k equal to 2 zeta r, and omega n square equal to k by m, and r equal to omega by omega n. So if we put these terms here, we will find x by y equal to root 1 plus 2 zeta r whole square upon 1 minus r square whole square plus 2 zeta r whole square under root. And according to the definition of the displacement or motion transmissibility, we say that it is the ratio of the amplitude of the response xt. So the amplitude of this response xt is capital X, and that of the motion of the base. So motion of the base is y sin omega t, so the amplitude is y, so x by y. So this is the, if we say transmissibility, displacement transmissibility, that is x by y, and this is equal to root 1 plus 2 zeta r whole square upon under root 1 minus r square whole square plus 2 zeta r whole square. So this is the formula for displacement transmissibility, and we see that the formula is same as the we obtained for the force transmissibility. Now the angle of lag between the xt and yt. So how much this motion x is lagging the y, so that is equal to phi minus alpha, and phi, we know that phi is tan inverse 2 zeta r upon 1 minus r square, and alpha is tan inverse 2 zeta r. Okay. So this is the angle of lag between the two motions. So we see that the angle of lag similar to what we obtained in the force transmissibility, that how much the transmitted force will lag the impressed force. So it is the same, and so there is the some relation between these terms. So here we can see the transmissibility curve again for the displacement transmissibility. Of course the curve, the nature of the curve will be same as we obtained in the case of force transmissibility. So here again we see that the curve start from 1 at r equal to 0, and it goes to maximas near r equal to 1, and again it drops and passes cross the transmissibility 1 equal to 1 at under root 2. So root 2, it is again being unity and going to the lower values of displacement transmissibility. And when we have r that is large, the transmissibility is lower. So this is the region where we are interested in this region, and as we discussed that this region is mass controlled, and so we have to stay in this region for lower transmission of the displacement to our mass m. Similarly, if we see the phase lag, so phase lag, this phase is starting from 0, and for zeta less than 0.5 it is going to some maxima and then coming and tending towards 90 degree, while for zeta greater than 0.5 there is no maximas, but directly they are increasing to 90 degree for r greater than for higher values of r. Okay. So, now we will do one problem based on the displacement transmissibility. So, we can see this example. We see that a radio set of 20 kg mass must be isolated. So, there is a radio set and it is kept on some vibrating machine. So, there is some machine that is vibrating, and on some that machine the radio set is kept, and the machine is vibrating with an amplitude 0.05 mm at 500 cycle per minute. So, it is given the vibration, that is y. The set is mounted on 4 isolators. So, that set is put on some isolators, each having a spring scale of 31400 Newton per meter and damping coefficient of 392 Newton second per meter. So, now it is asked that what is the amplitude of vibration of the radio and what is the dynamic load on each isolator due to the vibration. So, let us do this problem. So, we have a radio set. So, it is like this system. So, we have this is radio set and it is put on 4 isolators. So, we have 4 isolators. Okay, so we have 4 identical isolators here, and this is mass m, this is radio. So, this is radio set and these are isolators. So, 4 identical isolators and each has some k and let us say k dash and c dash, some values each. So, m is given 20 kg and the y equal to y sin omega t. So, y is given 0.05 mm and then it is 500 cycle per minute. So, omega equal to 2 pi into 500 by 60, this is radian per second. So, we can calculate and write here. Then the set is mounted on 4 isolators. So, we have 4 isolators each having a spring scale. So, k dash, that is the spring constant for one spring, is 31400 and damping coefficient c dash is 392. What is the amplitude of vibration of the So we want, so let's say this has some motion like x t. So we want x, so because x equal to x sine omega t minus plus alpha minus phi. So we want x and we want the dynamic load on each isolator. So these are isolators and there will be some load coming from the mass. So what is the force on each isolator? So we want F dynamic on each isolator. Okay. So now we have these 4 spring in parallel and 4 dampers in parallel. So we can write the combined stiffness is 4 times k dash. So 4 into 31400 and C equal to 4 times C dash. So it is 4 into 392. So we can calculate. So first we calculate omega. So it is so it is 52.36. So it is 52.36 radian per second and K is 4 into so it is 125,600 Newton per meter, and then the damping is 4 into 392, so 1568 Newton second per meter. So we have to find x. So as we have already today derived this relation x by y equal to root 1 plus 2 zeta r whole square upon 1 minus r square whole square plus 2 zeta r whole square under root. So to find x, and we know y, we have to find zeta and r. So zeta equal to c by cc, that is c by 2 root k into m. So it is c is 1568 by 2 root k is 125,600 into m, and m is 20 kg. So we can compute this. So we find zeta 0.495. Okay, so we have this damping factor. Now we have to find r equal to omega by omega n. And what is omega n? So omega n is root k by m. So root k we have 125,600 and m is 20. So we find it is 79.25 radian per second. So r equal to omega we have calculated 52.36 by 79.25. So r is so it is 0.66. So now we have r, we have zeta, we can put in this equation. So x by y is 0.05 mm. So we will get x in mm equal to under root 1 plus 2 into 0.495 into r. So r is 0.66 square upon 1 minus 0.66 square whole square plus 2 into 0.495 into 0.66 square under root. So equal to so it is 1.602. So x equal to 0.08 mm. Okay. So we are getting x equal to 0.08 mm. Now here we see that the x is greater than y means the more displacement amplitude motion is transmitted, more displacement is transmitted to the mass than what is coming to the base. Why? Because we are in r equal to 0.66, r less than 1, and when we are r less than 1, we are in the damping control region, and there usually we are above transmissibility more than 1. So now we want to know what is the dynamic load on each isolator. So first, what is the dynamic load? So the dynamic load, so the total dynamic load first we compute, then we will find for each isolator. So dynamic load comes due to the inertia force of the mass. So this mass has the inertia force m omega square x. So that is m omega square x. M is 20 and omega we have 52.36 square into x. X we have got 0.08 into 10 power minus 3. So we will get, so it is coming about 4.4 Newton. So because there are 4 isolators, so the dynamic load on each isolator equal to 4.4 by 4, that is 1.1 Newton. So here we see that the application of this concept in the vibration reduction or vibration isolation of the some sensitive article, okay, or like radio set or some instrument. So I thank you for attending this lecture, and let's see in the next lecture. Thanks.